All right, we've come to our last lesson this semester, and we're looking at hypothesis testing again. So same concept, same everything general that we did back in chapter 8, but now we're looking at hypothesis testing at estimating population means or using it to make predictions about population means rather than proportions. So the first part here, what we mean by a one-sided or a two-sided test, it's the same as what we were doing earlier. Remember, we're looking for making an estimate about the population parameter mu. Remember that mu is the population mean. And so our hypotheses, remember, are always statements about the population, whatever that is. So if it's a two-sided test, then our null hypothesis is going to be that mu equals some number. I'm going to call it mu naught this time. And then my alternative would be that mu does not equal, just like in the previous part of the course, mu does not equal whatever number we're comparing it to. If it's a one-sided test, a left-sided test, oops, sorry, this should be O, then mu would be equal to, for our null hypothesis, and our alternative would be that mu is less than whatever number we're comparing it to. And then if it's a right-sided test, our alternative would be the same thing, mu equals, and then, I'm sorry, the null hypothesis, and then the alternative would be that mu is greater than. Okay, so the structure of all of these is exactly the same as it was earlier in the course. Take a look at these pictures. So you can see the first one would be a two-sided test, the second would be a left-tailed test, and the third one would be a right-tailed test. Our preparation steps are getting ready to do our hypothesis tests are exactly the same as they were back in chapter 8. You're going to start off by stating your hypotheses. You're going to prepare by choosing a significance level. Remember, that would be your alpha. Usually, remember, we use 5%, but sometimes they'll tell you to use something else. Figure out your test statistic, which was the z-score. Now it's going to be a t-statistic instead, but it's the same idea. Check conditions and state any assumptions. Compute, which is usually going to be done in StatCrunch. We're going to find the p-value just like we did earlier. We want to decide if that p-value is smaller than our significance level, and then make a decision on whether or not to reject or fail to reject the null hypothesis based on that p-value. All right, so what do we need to check for? The sample has to be done randomly, so as long as it's a random sample, we know we're good to go there, and it's got to be large enough to be at least 25. So n has to be greater than or equal to 25, just like it did when we looked at confidence intervals. So our test statistic this time, we call it a t-score, and it's going to be the same as what it was when we looked at confidence intervals. T is going to be equal to x bar, our sample mean, minus mu naught divided by our standard error. So really similar to what we did in the previous part of this unit. Our standard error, we're going to calculate that the exact same way we did, like I said, with confidence intervals. It's going to be our sample standard deviation divided by the square root of n. If the conditions hold, the test statistic will follow a t-distribution with degrees of freedom, and remember, degrees of freedom is always n minus 1. The t-statistic measures how far or how many standard errors, just like it did in the previous part of the course, standard errors we are away from our observed mean x bar. Or, I'm sorry, away our observed mean x bar, so what we're looking at in our sample mean, how far away that lies from what we expected it to be, which was mu naught. Values far away from 0 tend to discredit the null hypothesis. All right, let's look at an example. In 2010, the mean years of experience among a nursing staff was 14.3 years. A nurse manager took a survey of a random sample of 35 nurses at a hospital and found a sample mean of 18.37 and a standard deviation of 11.12. Using the four-step process, determine if we have evidence that the mean years of experience among nursing staff at the hospital has increased using a 5% significance level. So our population would be all nurses, right? So all nurses at the hospital. We took a sample of how many nurses? 35, but we want to use that to estimate the experience level for all nurses at the hospital. So 14.3 was what we were comparing to in 2010. So that's going to be mu naught and so that would be a parameter. 18.37 was our sample mean, so that's going to be X bar, and that's going to be a statistic. And then 11.12 was our sample standard deviation, so that's S, and that's going to be a statistic as well. N is 35, that's our sample size, that's a statistic as well. So our null and our alternative hypothesis. So our null hypothesis, remember it's the status quo, nothing has changed. The population mean is still at 14.3. That's what we're comparing it to. The alternative, remember, you phrase that, or you set that up based on the phrasing in the question. Has the population, or has the experience level increased? So that means we want to know if mu is greater than 14.3. That's what we're comparing it to. We were told that it was a random sample, and N is greater than 25 because N was 35, so we are good to go with our sample size. All right, find the estimated standard error. So our estimated standard error, we're going to use that formula we had a few minutes ago. That's going to be S divided by the square root of N. And so in this example, S was 11.12 divided by square root of 35. And I have that number, that's about 1.88 standard errors. The test statistic is going to be X bar minus the mu naught that we expected divided by the standard error that we just estimated. So X bar, remember X bar was our sample mean of 18.37, and mu naught is the 14.3 that we're comparing it to. So 18.37 minus 14.3 divided by the 1.88 that we just calculated, and I'm getting about 2.16. So think about what would you say, 2.16? Do you think that's unusual or not? This would be the number of standard errors. Our observed sample mean is above what we expected. So interpret the test statistic. What could we say? The observed sample mean, so the observed sample mean, and I'm going to just remind us what that was, of 18.37, is 2.16 standard errors, I'm just going to abbreviate, standard errors above the expected mean of 14.3. All right, so let's draw a little picture here of what this would look like. So in the middle is what we would expect. So the middle was the 14.3 that we were comparing to. What we actually got was 18.37. So 18.37 was a little bit more than 2. So I'm going to put 18.37 right here. So we're up here somewhere. And because this was a right-tailed test, remember what the alternative was? Mu, it was greater than 14.3. That means I would shade to the right. So the p-value that we're going to calculate in StatCrunch, we're going to shade to the right. That's going to be this value right in here. So our p-value is going to be the shaded area right here. What is the degrees of freedom? Remember that our sample size was 35, so that means our degrees of freedom, remember it's n minus 1, so in this case it's going to be 34. And we're looking for the probability that we are above 18.37. If we labeled this in terms of our t-scores, our t-distribution, this would have been a t-distribution. This would have been a t-value of 0 right in the middle, and this would have been a t-value of 2.16. That was our estimated t-statistic from earlier. So we could say we're looking for the probability that we are above 2.16 is what we're looking for. That's our p-value. So let's go ahead and go to StatCrunch. Here's your steps for StatCrunch, so make sure you remember this. It's just like we did confidence intervals yesterday. It's going to be the exact same idea. So let's go into StatCrunch. We're going to go to Stat, T-Stats, one sample with summary. And I'm going to put in my sample mean, which I believe was 18.37, and my sample standard deviation, which I think was 11.12. And my standard sample size was 35. Now you do have to adjust your hypotheses to what you're interested in. So my null was that mu equals 14.3. My alternative was that mu was greater than 14.3. So I'm going to click on compute, and here is my information. My test statistic is what I calculated by hand, 2.16. You're not going to have to do the test statistic by hand every time. We can use StatCrunch to figure it out most of the time, but I do want you to see that it is what we calculated. And here is the corresponding p-value. So 0.0187 is my p-value. So let's fill that in. So the p-value is 0.0187. All right. Let's see. 0.187. Yeah. All right. Interpret the p-value. The p-value tells us that there is, and this is a percentage, don't forget. Remember what the p-value is. It's the probability of getting your particular sample or something more extreme if the null hypothesis is true. So in this case, it's the probability of getting, so the percent chance of getting, I'm going to change this to a percent, 1.87%. 1.87% chance of getting a sample of 35 nurses with a sample mean years of experience equal to 18.37. And I really should say or more here, or more, if the null hypothesis is true. So if the mean years of experience for all nurses is actually the 14.3. So the likelihood of getting our particular sample or something more extreme, if the real number of years of experience is 14.3, the probability of that occurring is only 1.87% chance. That's very, very unlikely, right? That's very small. We have a small p-value. So we're going to reject the null hypothesis because the p-value is less than the alpha level of 5%. Remember, 5% was our significance level. I don't know if they actually gave us a 5% significance level in the problem. Oh, they did. They said up here to use a 5% significance level. Even if they didn't give that to us, though, 0.0187 is so small, it's not going to matter. So we're going to reject the null hypothesis. So we reject the null hypothesis. There is sufficient evidence. Let's say there is sufficient evidence to support that the mean years of experience among nursing staff at the hospital has increased. So if we reject the null hypothesis, that means we have evidence that supports the alternative. And remember, the alternative was that the mean number of years of teaching experience has increased. All right, let's try the next example. In the United States, the population mean height for 3-year-old boys is 38 inches. Suppose a random sample of 15 non-US 3-year-old boys showed a sample mean of 37.2 inches with a standard deviation of 3 inches. The boys were independently sampled. Assume that the heights are normally distributed in the population. We'll run a hypothesis. All right. Okay. All right. So we'll run a hypothesis test to determine whether population mean for non-US boys is significantly different from the US population mean. All right. So the population, who is the population that we're interested in looking at? Well, it looks like we're looking at comparing boys that are not in the United States, it looks like. So we'll say all non-US 3-year-old boys is who we're looking at the heights for, okay? Identify the following values. So let's go through what we had again. So the population mean height for 3-year-old boys is 38 inches. 38 is what we're comparing to because it says run a hypothesis test to determine whether the population mean for non-US boys is significantly different from the US population mean. So we're comparing to this 38 inches. So that means that's our mu naught, which means that's the parameter that we want to compare to. We pulled a sample of 37.2, so that means that's our X bar. Sample mean is 37.2, which is a statistic. The sample standard deviation was 3, so that would be S, which is also a statistic. And then our sample size was 15, so N is 15, which of course would also be a statistic. State the null and the alternative. So the null hypothesis is that the mean is going to be 38 inches that we're comparing it to. The alternative, because it said different from, the alternative then is that mu does not equal 38. Verify that the conditions for the population are met to run a hypothesis test. That we were told that it was a random sample. We are good. Now, did we have a large sample? Actually, we did not have a large sample. N was only 15. Remember, 25 is our cutoff for a large sample. However, they did tell us in the question that the heights are normally distributed. Heights are generally going to be normally distributed. So because the heights are normally distributed in the population, we are good to go because we had a normally distributed population. So yes, the conditions are met. So let's go ahead and go into StatCrunch. We're going to go through the same process. So we're going to go to, let's see, let me go back up here. I'm going to close this out and do it again. We're going to go to Stat. We're going to go to T-Stats, one sample with summary. So my sample mean was, let's see what it was, 37.2. And my standard deviation for my sample was 3. My sample size was 15. My hypothesis, my mu was that mu was 38, and then it was a two-sided hypothesis, so not equal to 38. Go ahead and click compute. And then here's the information that I need. I've got degrees of freedom of 14. My t-stat is negative this time, which we would expect because my sample was 37.2, which was below 38. So my observed sample mean was below what I expected. So let's write these things down here. So my sample mean was 37.2. My standard error from StatCrunch was 0.775. My degrees of freedom was 14, and my t statistic was negative 1.03. And then my p-value is 0.3192. All right, so what do you think about that p-value? What do you think about that p-value? Is that small? It's about 32%. It says label the graph with the given test statistic and shade the appropriate area. So if we're doing it with t-scores, my t-distribution, 0 would go in the middle. My test statistic was negative 1.03, so that would go like right here, negative 1.03. Now, this was a two-tailed test, right? Because my alternative was that mu is not equal to the 38. So that means we're going to have one on either side. Remember, when it's two-tailed, you're going to have one on either side. So we're shading in this area here, but then we're also going to shade in 1.03, the same thing, symmetric on the other side, same test statistic on this side. And pretend those are symmetric. We'll pretend those are about the same. So remember, your p-value is, when you have a two-sided test, your p-value is the sum of both of these areas added together. So our p-value is that 0.3192 number that we got up here from StatCrunch. So what do you think? So let's see. The p-value tells us that there is so the p-value is 0.3192. If we change that to a percentage, that's 31.92%. There is a 31.92% chance of getting a sample of 15 non-US 3-year-old boys with a sample mean height of 30. What was my sample mean? I forgot what it was. My sample mean was 37.2. So 37.2 or less, or let's see, 37.2 or less, or let me see what I'm trying to say here. 37.2. Okay, let's back up. The way this is phrased, they actually want the numbers here, 37.2. So it wouldn't be 37.2 or less. What I need the number on this side as well, is what I'm trying to say. So to fill in the rest of this statement. So 37.2, so if we write this in terms of the original heights, 37.2 was the original height. 38 was what we were comparing it to. What would this number be on this side? So what is the difference between 37.2 and 38? So 37.2, let me write that a little neater. 37.2 and 38 is a difference of 0.8. So there's a point, this sample was 0.8 lower than what we actually expected. So that means the difference on this side needs to be the same. So this would be 38.8. Make sure you see where I'm getting that number from. If my sample was 37.2, that means it was 0.8 lower than what I expected of 38. So on the other side, my other possible extreme value, because it's a two-tailed test, remember, has to be the same distance on the other side. So this was 38.8. So to fill in this sentence, we're going to say 37.2 or less, or 38.8 or greater. And that's where I'm getting that number from. If the null hypothesis is true, right? So if the mean height of all non-US 3-year-old boys is actually, what was the null hypothesis? 38 inches. Would we reject or not reject the null hypothesis? Well, that p-value is large, so we would not reject the null hypothesis. We've got a large p-value, right? P-value is 32%. I don't care what your significance level is. It's never going to be larger than that. So what's our conclusion? So since we don't reject the null hypothesis, that means we don't think the alternative is true. We think that the null hypothesis is probably true. So what can we say? We do not have sufficient evidence to conclude that the height of all non-US 3-year-old boys is different from the 38. So we think boys in other countries, their heights are about the same, right? Probably no reason to think they'd be different. So that kind of makes sense from a biological standpoint. But we don't have evidence. Based on our sample here, we don't have evidence. So we don't have any evidence to indicate that the height of non-US 3-year-old boys is any different from this 38 inches that we had for American boys. All right, continuing from this example, now suppose the researchers had used a sample of 30 non-US boys instead of 15, but everything else stayed the same. So let's go into StatCrunch and let's make some changes here. So I'm going to go to Options, Edit. Sample mean, standard deviation was the same, but they're saying now our sample size was 30. So it's going to change our degrees of freedom. Notice our degrees of freedom now is 29. Our standard error has changed and our t-stat has changed. So let's go ahead and fill this information in. So my sample mean is still 37.2. That did not change. My standard error is going to be 0.4577. I'm sorry, 54. I said that backwards. 0.5477. Degrees of freedom is now 29. And my t-stat is negative 1.46. A little bit more extreme. Notice then the p-value got a little bit smaller as we expected. It got down to 0.1549. Right? We got a more extreme test statistic, which means we have a smaller p-value. So let's label the graph this time. So my 0 would go in the middle. My test statistic now is a little further towards the tail, negative 1.46. On the other side, we'll put positive 1.46. So if we were shading, my p-value would be here and here. Remember, because this was a two-sided test. What happened to the test statistic? It got more extreme. Okay, I'm not going to say larger because it's a negative number. I like the word extreme better. It got a little bit more extreme. It went a little further into the tails. What happened to the p-value? The p-value got smaller. Explain why the t-values and the p-values are different from the example that we did previously. So because we had a larger sample, right? We had a larger sample. That meant we had a couple of things. That meant we had a smaller standard error. That also meant we had more degrees of freedom. So higher degrees of freedom mean that your tails are going to be thinner. And so if your tails are a little bit thinner, that means we've got less p-value. Okay. All right. So a larger sample size meant we had a smaller standard error. We also had higher degrees of freedom, which means that our tails ended up being a little bit thinner, and that gave us a smaller p-value. All right, let's try this one. Suppose that 200 statistics students each took a random sample of 50 students at their college and recorded the ages of the students in their sample. Okay, let's take a look at that. So let's see. So our sample size, let's just write a few things down before we get too into the problem. Our sample size, n equals 50. Each student, let's see, 50 students is our sample size. Each student used his or her data to calculate a 95% confidence interval for the mean age of all students at the college. How many of the 200 intervals would you expect to capture the true population mean age? And how many would you expect to not capture the true population mean age? Okay, I was thinking they were asking us to actually calculate a confidence interval, but that's not what they're asking. So they're saying basically if we repeatedly took 200 samples, so we did 200 samples of 50 each. Okay, so we're going to do sample 200 times. We're going to compute a 95% confidence interval. How many of those would you expect to capture the true population mean? So remember what the confidence level tells you. 95% confidence interval tells you that 95% of those samples should include the true population mean. So 95% of the 200 should include population mean, whatever the real population mean is. So I'm going to do 95% of 200, and I'm getting 190. So basically 95% of 200 means that 190 of those samples should include the true population mean, whatever it ends up being. All right, a 95% confidence interval for the ages of the first 6 presidents at their inaugurations. Let me see, 95% confidence interval for the age of the first 6 presidents at their inaugurations is between 56.2 and 59.5. Either interpret the interval or explain why it should not be interpreted. It's kind of a silly question here. And the reason, I would say this should not, why would we do a confidence interval on this? Because I would say we should not do a confidence interval on this, right? A confidence interval is not necessary here. Why is a confidence interval not necessary? Confidence interval is not necessary. I can't spell necessary. Necessary. Why? Because we're talking about presidents' ages, because we know all of that information. So we know the president's ages. I'm not sure if I guess we're trying to, the idea is you'd be using a 95% interval to estimate the ages, average age of all presidents, but we know that information anyway. We know, I'll say that, we know all presidents' ages. So there's no need to compute a confidence interval if you have information about your entire population. In this case, if our population is all of the presidents that we've had so far, we know their ages. That's all been recorded. So there's no need to compute a confidence interval here. And I think that's what they're trying to get you to say in this question.